Assalamualaikum warahmatullahi wabarakatuh dan selamat sejahtera. Today we're going to learn on the dynamic process behavior of the chemical process control. Basically, we have learned all those process component of the process control loop that include the sensor, transmitter, and then controller, and finally the control valve, which is the final control element of the process control loop. So on this week, we're gonna learn of the dynamic response of the process control loop, which it can be in linear first order or second order or higher order differential equations. So our objective is to learn how the parameters of the first order system and second order system affect their response, so that later we can infer the important characteristic of the response of the system by simply examining its transfer function. First order system are also important because many higher order systems can be treated as combination of first order system in series or in parallel. Changes continuously happen in process time. So the changes is due to process requirements, the increment and decrement of production volume, parameters, and many more that cause the changes in input. So as we know that changes in input is linear with the process response. So the changes of input could be in many types, but the one presented in the slide are the most type that we can find in chemical process control. So the first one is the step changes. As you can see from the slide. So this is the step input changes, where it has a magnitude right after the changes has been made to the controller. And then this is the RAM. The increment, there is a slope of RAM type of input changes. And then rectangular pulse input, you can see this is the kind of pulse input changes. And then the sine wave, the trend is like a sine chart. Now we look at the most common effect changes, which is the step input. So the example of the step input changes is, for example, there is a reactor in your plant. This is the reactor. So there is some disruption on the feedstock, which is the flow into the reactor. So the disruption causing sudden changes in feed concentration, flow, pressure, and temperature of the inlet stream to the reactor. Okay, we take the example of the temperature. For example, the first steady state temperature is, for example, at 70 degrees C. Alright, and then when there is sudden changes, for example, the temperature is reduced to 50 degrees C. Alright, so a sudden changes in a process variable can be approximated by a step change of the magnitude. So this is the magnitude from the initial steady state to a new steady state. So at time equals to 0, the magnitude will be 0. This is at time 0. Time 0, where there is no changes happen to the steady state of the process control parameter. And this is where at the time that there is a changes happen in the input stream of your reactor, reducing from 70 degrees C to 50 degrees C. So at time more than 0, maybe at 2-3 seconds, for example, your magnitude can be measured by m. Alright, and then the step change occurs at an arbitrary time denoted as t equals to 0. And there is a special case if m equal to 1. We have a unit step change. So we get a symbol as a st. Alright, so now we try to solve differential equation that represent dynamic of process and their control system. So the objective is to find how this output signal respond to the input forcing function. We assume that initial conditions are at steady state, where at 0 time derivative, and define all variable as deviation from their initial value. This forces the initial value of the deviation variable also to be 0. So given that the first order differential equation as follows, where a1 dy t divided by dt plus a naught yt equals to bx t plus c, where yt is the output of the dependent variables, and then the xt is the input variable, t is time, the independent variable, and the parameters a1, a naught, b, and also c are constant. Alright, this one is constant. Sorry, this one constant. This one constant, and this one also constant. And we can write the equation at the initial steady state, that is before any changes in input xt take place. Alright, so this is the equation. A naught y naught equals to bx plus c. Note that this equation establishes a relationship between the initial value of x and y, and then you need to subtract first equation to second equation. Alright, so in order to subtract, you need to do this arrangement. So a1 dy t over dt plus a naught yt minus a naught y0 equals to bxt minus bx0 plus c minus c. Alright, so you can cancel off c and then gather the equation. Equals to bx t minus x0. Alright. And then substitute the derivation variables into this equation. The derivation variables is y t equals to y t minus y naught, and then x t equals to x t minus x naught. Alright, so replace this into this. Alright, after you replace the deviation variables into the subtraction equation that you got before, so you will get this equation. We name it as equation 3. So equation 3 is the general linear first order differential equation in terms of the deviations of the input and output variables from their initial steady state value. So it has three coefficients, which is the a1, a naught, and also b. But without loss of generality, we can divide the equation by one of the three, so that we can characterize the equation by just two parameters. Alright, so for example, we divide by a0, a1 over a0 dyt dt plus a naught over a naught y function of t b over a naught x function of t, and then replace this alright, into this, and k into this. So you will get this equation. Tau dy over dy t over dt plus y, so this is equal to 1, yt equals to kx as the function of t. And then we further substitute the certain term dyt ds and kxt with the transfer function of linear property. Alright, so you can refer the Laplace transform of the linear property, and then you'll get this equation ts ys plus ys equals to kxs. Alright, and then rearrange the equation. Alright, and then you will get the general first order transfer function. So the equation stated the first order differential equation, which is the ys equals to k divided by tau s plus 1 times xs. Alright, so the term in bracket is the transfer function of the first order system in standard form. So the characteristic of this form is that the second term in the denominator is unity. So when the transfer function in this form, the numerator term is the gain, and the coefficient of s is the time constant. So k is the process gain. Process gain is the model parameter that describes how much the measure output y changes in response to changes in input x. Okay, and tau is the time constant. The time constant can be obtained from the value of time in which the response is 63.2% complete. The response of a first order system is monotonic. What we know monotonic is this kind of process response curve that is stable if its time constant is pressure. So to find the time constant, as I explained before, it is the 62.2% of the x-axis. So this is how you need to find a value at 0.632, and then draw a horizontal line touching the process response curve and bring it down here, and then you will get the time constant. All first order system forced by a step function will have a response of this same shape. Alright, so for all first order system, the shape will be this kind of shape. And to obtain the step response of magnitude delta x, so we transform the input xs from the general transfer function of the first order differential equation. We replace xx equals to delta x divided by s. Alright, we change xs into the delta x over s. Next, we would like to determine the process gain. Just now we have identified the time constant from the process response curve. Now we're going to identify the process gain. Process gain can be used to determine the ultimate value of the response, which is the new steady state for a unit step change in an input. So to calculate process gain, k is equal to delta y. Delta y is the new steady state obtained from the process response curve, and while delta x, alright, delta x is the changes made in the step input. To obtain the ultimate value of the output from the transfer function, you can use this formula. Y is equal to gain multiplied with the change in magnitude x. This is how you find the ultimate value of the output transfer function. For the exercise 1, consider a first order process with the transfer function ys over xs equal to 4 divided by 5s plus 1. Determine the ultimate ultimate value of y when a step change with magnitude of 4 is introduced into the process. So to find the ultimate value, y is equals to gain multiply with the magnitude x. So in order to find the ultimate gain, so your gain will be 4 times the change in magnitude is given in the question, which is 4. So the ultimate value of y is equals to 16. Some process responses exhibit time delay, also known as dead time or transportation lag. So this is the time delay. By the real translation theorem, the time delay will modify the standard first order transfer function as equation below. Ys equals to k e power of minus st naught divided by tau s plus 1 times xs, where t naught known as time delay or dead time, where the delay from when an input signal is issued until when the output y begins to respond. The term in bracket, alright, the term in bracket is an important transfer function used to approximate the response of higher order reaction. So this is the important term that can approximate the higher order of process. By definition, process dead time or time delay is a period of time between the starting of input load change and the intersection of tangent line and all steady state baseline. So this is your process response curve. Alright, this is your process response curve, and you get the all steady state baseline, or known as a lower baseline. Alright, so this is your old steady state, and then this is your new steady state where the process response start to achieve the set point. Okay, so what you need to do is you need to draw a lower baseline at the old steady state value, and then you need to also draw the tangent line. So this is the tangent line. You need to find the maximum point of the process response curve, and then draw a tangent line along through the process response curve. Alright, so in order to find the time delay, okay, time delay is at starting input load change. Okay, starting input load change. Okay, you refer to the step change input. Alright, so this is at the point at which the input start to change, and also the intersection of the tangent line and also the old steady state baseline. So this is the intersection between these two, tangent line and also the old steady state line. So the range of time delay is between here, starting point of the input changes, and intersection of the tangent and also old steady state baseline. By definition, time constant is a period of time between t at PV at 62.3% and the time at cross section of all steady state baseline and also tangent line. Previously, you have been introduced to the old steady state baseline. Alright, so this is the old steady state baseline. This is a new steady state baseline. Another one parameter that you need to identify in order to determine the time constant, also time delay, is also the tangent line. So tangent line, you need to find the maximum value at maximum value and then draw a straight line. Okay, so this is your tangent line. Okay, so to find time constant, you need to find first time at PV at 62.3. So how do you find 63.2? Okay, so you need to find the differences between the old steady state. Alright, So you need to find the differences between the new steady state baseline and also old steady state baseline, or as delta y. And then to find TPV, to find PV at 62.3%, you need to identify the PV at 63.2. So to identify PV at 63.2, all right, 3.2%, you need to find using this formula, 0.632 times delta y. So delta y is the range between the new steady state baseline to the old steady state baseline. Alright, so up to here. Okay, so when you get the value, alright, for example, delta y is equal to 100. Okay, so you will get 100, 1, 2, so 63.2%, for example. So after 63.2%, you identify the location of PV at 63.2, and then you need to draw a horizontal line, okay, until it is touch the process response curve and bring it down to below. So after that, you can identify T at PV equal to 63.2%. So remember, in order to find time constant, so time constant, you need to find TPV 63.2. This one you have identified earlier, and then TD. How do we find TD? As mentioned earlier, it is at where the point of step input change into the intersection of the tangent and also the old steady state value. So after you identify TD, plug in into the equation, and then you'll be able to identify TC at 63.2%. Figures show the process response curve after a change is made to the set point at 10%. You need to estimate the dead time, which is the TD, constant time, TC, and also gain of the process. You need to write down the transfer function for first order differential equation as well. To solve exercise 2, this is the step-by-step given in order to guide you to solve this exercise. So the first one is you need to locate a maximum gradient. So how do we locate a maximum gradient? So as a guardian, this is the maximum gradient. So next you need to draw a tangent line at maximum gradient. So this is your maximum gradient, and draw a straight line, point A to point B. Alright, point A from point B. So this is known as, this line known as a tangent line. Next, you need to draw a straight line at PV at all steady state value, and it is known as a lower baseline. So how do we find the old steady state value? The old steady state value is at this point. So draw a straight line, and this is known as the lower baseline. Alright, next you need to draw the straight line at PV at new steady state value. So new steady state value, where this is the new steady state value. So you need to draw a straight line. Okay, so this is your upper baseline. Upper baseline at PV at new steady state value, and then you need to calculate the in order to find the PV at 63.2%. Alright, so you need this formula. Alright, how do we find? You need to find the value. Alright, this is PV. Identify, locate PV at PVNSS minus PV at OSS. This is OSS, this is NSS. So find the PV at 63.2. And then after you get this value, for example, the value is y. So locate the value of y. For example, this is the value y. This is y value. So this is the PV at 63.2%. Draw a straight line until it touch a process response curve and bring it to the x-axis, where uh, draw a vertical line and bring it to the x-axis, and then you bring the line to the x-axis, and then you can solve the time. You can find the time at PV at 63.2%. Alright, so this is your value. So in order to find the time constant, you need to locate TD. How do you locate TD? TD is the intersection of the tangent line with the lower baseline. This is your TD. To find time constant, TP at PV 62.2% minus TD. So this is your TC. Alright, so you can solve TD, TC, and also gain. So how do you find a gain? Please refer back to the previous equation. So what is the formula of gain? And you can solve the gain. After that, you can write down the transfer function for first order differential equations. Please try to solve this equation and submit at Google Classroom. A linear second order system is one represented by a linear second order differential equation. A general form is represented in the equation A2 d square yt divided by dt square plus a1 dy t over dt plus a naught yt equals to bxt plus c, where yt is the output variable, and then xt is the input variable, and the parameter of a2, a1, a0, b, and also c are constant. Assuming the initial condition are at steady state, and the equation at the initial condition is equal to a naught y naught equals to bx naught plus c. So this is your first equation, and this is your second equation. Same with the first order system. We need to subtract equation 1 to equation 2, and then you should be able to get this. E2 d2y t divided by dt square plus a1 dyt divided by dt plus a naught y t minus a naught y0 equals to bxt minus bx0, and then plus c minus c. So this one can be cancelled off. C minus c is equal to 0. a2 d2y t divided by dt squared plus a1 dyt equal to dt plus a naught yt minus y naught equals to bxt minus x naught. Similar to the first order system, you need to replace certain term to the deviation variable which are y equals to yt minus y0 and xt equals to xt minus x0. After you replace the equation, the subtraction equation with the deviation variable, so you will get this equation: a2 d2 yt divided by dt square plus a1 dyt divided by dt plus a0 yt equals to dxt. So this is the equation you obtain when you replace the subtraction with the deviation variables. And after that, you need to divide this one with another constant, which is, for example, we take at a0. So a2 divided by a0, a1 divided by a0, and then a0 divided by a0, and bx divided by a0. Alright, and then you replace this one with this characteristic time, and then lambda is the new term that has been introduced into the second order differential system, and also k is the gain at the steady state. So k, you place here k x t. Alright, so this one you only get yt. Alright, cancel off, and this one you need to replace with lambda. Alright, so lambda is equals to a1 divided by 2 t naught, a1 divided by 2 tau a naught. So if you rearrange into this equation, so you will get a1 a naught equals to 2 tau lambda. Alright, so replace into this one, so you get 2 lambda tau dy, 2 lambda tau dyt divided by dt. Alright, so a2 divided by a0. So if you rearrange this equation, you get tau square equals to a2 divided by a0. Right, so tau square d2 yt divided by dt square. Alright, so this is the equation that you get. Next, you need to replace the Laplace transform and apply the linearity property and the real differential theorem. And yeah, after you solve the theorem, it will transform into the output as this one. Alright, transfer with the Laplace transform, you will get tau squared s square ys plus 2 lambda tau s ys plus ys equals to kx s. Rearrange this equation, then you will get the general second order transfer function. Ys equals to k tau 2s2 plus 2 lambda tau s plus 1 x in the function of s. So the term in the bracket is the second order transfer function in standard form. First order systems are also important because many higher order systems can be treated as combination of first order system in series and parallel as mentioned before. As shown in the figure, the transfer function of second order differential equation composed of two first order subsystems, which is the G1 and also G2. So the transfer function for second order system that composed of two first order subsystem is given by K1 times K2 divided by tau 1s plus 1 times tau 2s plus 1. So as we know that this is the transfer function for first order differential equation, K divided by tau s plus 1. So the condition of stability is satisfied if and only if the damping ratio is positive. So this is the damping ratio. We can now see that the term damping ratio refers to the damping of oscillation. So the behavior of the response as follow. If the damping ratio larger or equals to 1, it is the response categorized under overdamp. So at overdamp, and it is monotonic and stable. So the response of monotonic is like this. If the value of damping ratio in between 0 and 1, it is categorized as underdamped. So it will have the oscillatory type of process response and also stable. And finally, the damping ratio is equal to 1. It is critically damped and it will sustain the oscillation towards the end of the set point. Now we look at the change in step response. So we assume that the input is a step change of magnitude AX. So you need to substitute the XS with the delta X divided by S if there is a changes in step response. So this is the figure showing that if the step response has been changed for the second order process. So if you refer this, the lambda 1 and then change to 1.5, change to 2, and subsequently in 3. So this is kind of the graph that change in when change in step response is made. Previously, if we have seen the figure for step response change for critically damped or overdamped for second order processes. Now we look at the step response change of the underdamped second order processes. So if you can see from the figure, if we change the lambda into 0.2, 0.4, 0.6, and 0.8, you will observe that the trend of the oscillatory process response curve has been changed into the overdamped type of process response curve. Certain terminology used in the second order step change differential equation. For example, the overshoot. What is the overshoot? So overshoot is a fraction of the final steady state change by which the first peak exceeds this change. So to calculate overshoot, OS is equal to A divided by B equals to exponential of minus pi lambda divided by square root of 1 minus lambda square. The second term is time of the first maximum. So it is known as TP. So what is TP? TP is the time required for the output to reach its first maximum value, and it is given by this equation, pi tau divided by square root of 1 minus lambda square. The third terminology is the decay ratio. Alright, so it is known as C divided by A. So what is the decay ratio? Decay ratio is the ratio at which the amplitude of the sine wave is reduced during one complete cycle, and it is given by this equation, exponential of square root of bracket minus 2 pi lambda divided by square root of 1 minus lambda square equals, or A square divided by B square. And then a value of P, which is the period of oscillation. Period of oscillation is defined by time between two successive peaks of the response, and it is given by this equation. E equal to 2 pi tau divided by 1 minus lambda square. And then the rise time, also known as TR. The rise time is the time taken for the process output to first reach the new steady state value. And finally, the setting time. So setting time is the time it takes for the output to come within the band of the final steady state value and remain in this band. So for exercise 3, A, B, and P in the second order response are 20 degrees C, 50 degrees C, and 6 seconds respectively. Determine the second order transfer parameters, which is the tau and zeta, and write down the complete second order transfer function. So use the general second order transfer function to solve this equation. So the hint to solve this question is you need to use these two equations, which is the overshoot and also the period, to find a value of zeta and tau. Please try to solve this equation and submit in Google Classroom. And either process response will behave exactly like the input change, where the response achieves set point in no time, and accurately at desired change with naturally is impossible. The process response behaves in various conditions as the input change shown in the slide. It could behave on the damped type of response as represented by green and also blue line, and also the overdamped shown as pink line. So one of the requirements that we would like to achieve in any event of step input change is a stable process response. So the process response is said to be stabilized at near the set point as represented by green line in the figure. The unstable process response, in the other hand, could not be stabilized at any set point. So this could be any factor, could be due by any factor such as large deviation in PID value from its optimal value and many more. Another important criteria in designing stable control system is by defining the quality limits of the process response curve. A quality limit is a range of set values above and below the set point, known as the upper control limit, represented as UCL, and lower control limit, represented by LCL. Within these boundaries, process response is allowed to oscillate, while exceed the limit would endanger product quality. Process response of the automatic controller would behave in various steps, such as QAD, also known as quarterly amplitude damping, oscillatory, underdamped, overdamped, and offset. The settling criteria depends on certain quality imposed by the objective of designing control system. Example of settling criteria for process response is response time. Some might looking for fast response with minimum time delay. Alright. Some, in other hand, might look for longer settling time, as some process requires some time to achieve complete conversion. Others, for example, looking for faster rise time. The response curve must in quarterly amplitude damping, for example, type of response. And the quality limits, for example, is not going beyond 20% for UCL and also LCL in order to ensure high product quality. For the temperature and pH controller, it should behave with no overshoot and undershoot due to its nature that require a longer time to increase and decrease. And many more of the settling criteria, and it again depends on certain consideration of the objective in designing process control for certain processes. In brief, to design an automatic PID control system, an open loop test will be carried out to identify certain control parameters, namely the response rate, RR, TD, dead time, and also TC, the time constant. PID value then calculated according to tuning rules using the process control parameters identified previously. PID value then applied to the controller, and several tuning activities implies to obtain optimum PID value. An optimum PID value would drive the process response toward the set point and certain settling criteria explained beforehand. That's all for today. Thank you. Assalamualaikum warahmatullahi wabarakatuh. And see you next week.